All right, guys, so this week we're going to talk about greenhouse gases. Just a reminder, make sure you guys email me your lab and submit it on Blackboard. For the air pollution lab, some of you guys only emailed it to me, and some of you only submitted it on Blackboard. Make sure you do both. I really need you to do both, okay? All right, so first, before we get into greenhouse gases, I want to show you guys this picture. So all of this black at the bottom of the screen down here, this is actually a picture from space, by the way. But all of this black down here, this is the Earth. And then all of the black out here on the top, this is outer space. And so this really thin little blue strip right here, this is what we know as the atmosphere. And so this is where all the weather happens, this is where clouds are, this is where planes fly, etc. All of that happens in this really thin little blue strip right here. And the next couple of labs that we're going to do is going to focus heavily on the atmosphere and things that occur in the atmosphere. And so I wanted to point this out to you so you at least have an idea of where we're working at right now. So this is where all of the stuff we're going to talk about today is going to take place at. It's this really thin little blue layer right here. So let's start really basic. Obviously, this is the Earth. This is the sun over here. And I guess the first question I want to pose to you guys is, where does all of the energy that we use on Earth come from? And if the picture didn't already give that away to you, the answer is the sun. Some of you may know a little bit about like geothermal energy and like some stuff that comes from like the inner part of the Earth, like the core and whatnot. That is very minor in comparison to what we get from the sun. And so, you know, for all intensive purposes, all of the energy that we use on Earth comes from the sun originally, okay? And so that is what this yellow arrow right here is denoting. So this is just the energy coming from the sun to the Earth. And we call that solar radiation or shortwave radiation. But that's just energy coming from the sun to the Earth. And we denote that with this S naught right here. This is not really important for you guys, but I would just want to go ahead and point this out to you. The reason we denote this energy as S naught is because we consider this to be a constant. So we consider the amount of energy that the Earth receives from the sun to be fairly constant. Now, obviously, this value does change a little bit over time, like with solar flares and solar cycles and things like that. But that value doesn't change very much, and over time it stays virtually constant. And so we call this the solar constant. But that's all this right here is denoting. It's just denoting the energy from the sun that's coming to the Earth. And what happens is the Earth absorbs all this energy. Now, in the next lab after the greenhouse gas lab, we'll actually talk about why the Earth does not absorb all that energy and how we lose some of that energy. But for this week, we're going to just make the assumption that the Earth absorbs all of that energy that comes from the sun. So the Earth absorbs this energy. And then another important concept that you guys should understand is that anything that absorbs energy or anything that has energy has a temperature. And anything that has a temperature emits radiation. And you guys fundamentally know this. So you know if you're in a room with 2 other people, it may be comfortable. If you're in a room with 500 people, you know that it can get really hot and it can get really uncomfortable because there's so many people. Every person has a temperature, and so every person is emitting radiation out into the room or wherever it is you're at. So the car, the elevator, whatever. And so the more people you have in that space, the more energy you're releasing into that space, and so the hotter it gets. And so the same is true of the Earth. The more energy that it receives, the more it absorbs, and the more that it absorbs, the warmer the Earth gets. And the warmer the Earth gets, the more energy that the Earth emits back out to space. And so that's what these red arrows are indicating. So all of these is just indicating that the Earth is sending radiation back out to space. So again, the sun sends energy to the Earth absorbs that energy and it heats up. Because the Earth has a temperature, it emits radiation, and it emits that radiation back out to space. Okay, so that's the setup currently that we have, and we'll modify this over time. Especially in the next week's lab, we'll modify this even more. But this is where we're going to start. We're going to start very basic here. And if you go through here and you do the whole energy balance, and this requires some math and some other stuff, so we're not actually going to do it together, but I've done it and have it here at the bottom. So this setup here of energy coming in from the sun to the Earth absorbing that energy, and then the Earth emitting that out to space. If you were to calculate the average surface temperature of the Earth using this setup, you would get that average Earth temperature is about 255 Kelvin that I have right here. And 255 Kelvin, just because I'm assuming most people aren't familiar with Kelvin that well. That equates to approximately -1 degrees Fahrenheit. So again, this whole setup that we have right now leads us to having an average Earth surface temperature of -1 degrees Fahrenheit, which hopefully you all know, like, wait, that seems like that's way too cold. There's no way that that's accurate. There's no way that the average temperature of the Earth's surface is -1 degrees Fahrenheit. And you would be right. This is not true. Now, there's nothing wrong with what we've done up here so far. There's a lot of things that we're missing, and we'll fill in some of those gaps, in just a second. And then also, again, like I said, next week we'll fill in some more of these gaps. But there's nothing wrong fundamentally with what we're doing here. It's not like our energy coming from the sun is wrong, or the whole concept of the Earth emitting energy out to space is wrong. Like, all of this happens and all of this is true. We're just missing some pieces that makes this number down here more realistic. So the first question and the first piece we're gonna fill in this week is, why is the Earth so cold? So why is it in this situation right here we get an Earth's surface temperature that's way too cold? Now, some of you may already know this answer. For the rest of you, obviously I'm about to give it to you. And it's going to go back to that very first picture that I showed you of the atmosphere. So again, this really thin blue strip right here is the entire atmosphere. And this atmosphere right here is the reason that the Earth is warm enough to support life on Earth. So this atmosphere, we say, basically acts like a blanket for the Earth. It keeps us warm enough for life and humans and plants and whatnot to function. It's all because of this atmosphere right here. Now, obviously, the next follow-up question to that is, how does the atmosphere act as a blanket, or why does the atmosphere act as a blanket? And that is what we're going to be talking about in this lab primarily, and that is going to be because of greenhouse gases. And so I think the ones you're probably most familiar with is obviously carbon dioxide. You may be kind of familiar with methane. Another big greenhouse gas is nitrous oxide. You may not have heard of that one. There's also some smaller trace gases that we're not really going to get into in this lab. This lab's primarily going to focus on carbon dioxide, but here's kind of the big three greenhouse gases that we talk about a lot, especially with like global warming and climate change and stuff like that. And if you look at these little descriptions, you can see pretty much all three of these come from, fossil fuels, oil, gas, coal, that kind of stuff. Obviously, methane, a big source of methane is like livestock and agriculture. So basically, those are the industries that a lot of these greenhouse gases come from. But there's one on here that you've probably never really talked about. And I want to bring this one up right now, and that is water vapor. So water vapor, for those of you who don't know, it's literally just the vapor form of water, so just the gas form of the liquid water. And water vapor is, obviously, it's in the atmosphere naturally. And this is actually the most abundant greenhouse gas. So there's more of this than there are any of these other ones that you hear about all the time. And water vapor is actually the reason that this situation right here does not occur. So again, in this situation, the Earth was way too cold. Now, if you add the atmosphere and all the water vapor that exists in the atmosphere, that is the reason that the Earth stays warm enough. So the water vapor that exists in the atmosphere is the reason that the atmosphere acts as a blanket and keeps the Earth warm enough for us to live. The reason that we don't talk about water vapor all that much when it comes to climate change and global warming, and actually that's not true. We talk about water vapor a lot, like amongst atmospheric scientists and climate scientists and stuff like that. But when it relates back to like policy and like the general public and stuff like that, the reason we don't talk about water vapor all that much is because water vapor is a natural greenhouse gas that exists in the atmosphere. It's not something that we're pumping into the atmosphere and we're adding to the atmosphere. So this is something that's already there naturally. These are things that we're adding, that humans add. And so this keeps us warm enough to survive. These lead to what we know as climate change and global warming and things like that. So how do those greenhouse gases act as a blanket? That's what I want to show you guys now. So the setup we had earlier was the solar radiation came down to the Earth's surface. The Earth absorbed that radiation. The Earth heated up. The Earth has a temperature, and so then the Earth emits radiation, and that's these arrows right here. And in the first setup, we basically said that the Earth emitted this radiation, and this radiation just basically escaped to space. Now we've added the atmosphere, and we've added the greenhouse gases that are in the atmosphere. So this is water vapor, methane, and CO2 is over here. And so what happens is when the radiation from the Earth gets to the atmosphere, these greenhouse gases actually absorb the Earth's radiation. And when the greenhouse gases absorb the Earth's radiation, that causes the temperature of the atmosphere to increase. And as we talked about earlier, anything with a temperature also emits radiation. And so if the atmosphere gets warm, the atmosphere is going to emit radiation. Some of this radiation you can see right here actually escapes to space, and we basically kind of like just lose that energy. The rest of that energy actually comes back down to the Earth's surface. And so now the Earth is not only being heated by the solar radiation from the sun, but it's also being heated by this radiation from the atmosphere. And so the combination of these two things right here is what keeps the Earth warm enough for all of us to live, and for plants and all that other stuff to live. And again, this right here is from water vapor. However, whenever you add things like methane and things like CO2, you're adding all of this extra heat source that's bringing all this extra heat back down to the Earth's surface. And that is what leads to the process that we talk about as climate change and global warming. So I want to show you this in this kind of a setup. So again, this is just the solar radiation coming down from the sun. It heats up the Earth's surface, and so because it heats the Earth's surface, the Earth has a temperature, and that's this T1. Because the Earth has a temperature, the Earth emits radiation. That's this black air right here. And actually, you can ignore this right here. You don't need to know any of this stuff right here. But anyway, the Earth has a temperature, and so the Earth emits radiation out to the atmosphere. Now, right now, we're going to assume that this is like a natural system. And so this right here, in between these dashed lines, is going to be our atmosphere. And we're going to assume that the only greenhouse gas that exists here is water vapor, because this is a natural environment. So we don't have any pollutants or anything man-made in the atmosphere. So the water molecule, or the water vapor molecules, they absorb this radiation coming from the Earth. And so because they absorb that radiation, now the atmosphere has a temperature, and that's this T1. And again, anything with the temperature emits radiation. So the atmosphere is going to emit radiation out to space, and it's also going to emit radiation back down to the Earth's surface. And so again, this right here is kind of the natural system, and this is what keeps the Earth warm enough. But now, let's say we add a bunch of other greenhouse gases to the atmosphere. So we release a bunch of CO2, a bunch of methane, nitrous oxide, and other greenhouse gases. So now the atmosphere is going to absorb more energy from the Earth. And if the atmosphere absorbs more energy, what's going to happen to it? Well, the atmosphere, the new temperature of the atmosphere, this T2, is going to be bigger than the original temperature, T1, in the natural setup. So all this means is that the temperature increased because the greenhouse gases are absorbing more energy from the Earth. So if the temperature of the atmosphere increases, what's going to happen to the amount of energy that the atmosphere is emitting? It's also going to go up. So now you have twice as much energy coming back down to the Earth from the atmosphere, and you still have the solar energy from the sun. And so the combination of these two effects leads to what at the Earth? What does this do to the Earth? Well, the new temperature of the Earth, this T2, is now bigger than what the original temperature in the natural setup was, T1. And so again, this is just showing you that if you add greenhouse gases, the atmosphere emits more radiation, and that's what causes the Earth to warm up. Now, if you kept this going, if the Earth is warmer, we know that the Earth is going to emit more radiation. If the atmosphere is getting more radiation from the Earth, the atmosphere is going to get even warmer. If the atmosphere is warmer, it emits more radiation, right? And if it emits more radiation, well, then the Earth gets warmer. So you can see this is a little cycle here. It's kind of a loop that just kind of keeps going in itself. And so this is one of the reasons why we're very concerned about climate and climate change and global warming and stuff. This is a very simple process that's kind of showing that feedback, that warming cycle that we're in. Now, there's a lot more that goes into this, and there's a lot of processes that go in here that we're not going to talk about. we're going to keep this very simple and straightforward for this lab, and this is really all we're going to talk about right here. If you're interested in any more of the details or any more of the complicated stuff, feel free to reach out and we can talk about anything you want to. But for the purpose of this lab, just to make it doable for everyone, this is as far as we're going to go with this. Another thing that I want to point out to you guys is one of the reasons that we're concerned about these greenhouse gases is not only because of this effect, and this is very important, this is a big concern of ours, but another reason is right here, their atmospheric lifetime. This is basically just how long these different molecules last in the atmosphere. And so you can think if you emit a molecule of CO2 into the atmosphere, you may think, oh, I emitted that to the atmosphere and tomorrow it's gone, or next week it's gone. Actually, CO2 can last in the atmosphere anywhere from 5 to 200 years. And this depends on some other factors. And again, it gets more complicated than this, so we're not going to get into all of this in this lab. But the point is that CO2 can last in the atmosphere for a long time. So methane is about 12 years. You can see some of these smaller trace gases. This one over here is up to 50,000 years. So these different greenhouse gases can last in the atmosphere for a long time. And so they can cause this process to speed up. If we keep adding more and more up here, stuff in the atmosphere from a long time ago, you can see if CO2 lasts in the atmosphere for 200 years, for example, you can see that stuff from 200 years ago could still be up here. Plus, we're continually adding more and more new stuff. And so this cycle right here is really sped up. And so this is the whole climate change and global warming stuff that you hear a lot about. This right here, this is just a plot. This one over here is CO2, and this one on the right is methane. And this is just showing you from the CO2s from 1975 to 2015. And this is just showing you the steady increase in the amount of CO2 in the atmosphere. And then this one on the right is from 1988 to 2016. And this one's just showing you kind of the fairly steady increase of methane into the atmosphere. For this lab, you're going to be working with this data over here on the left. And so this over here is going to be kind of the focus of the lab. It's going to be this CO2 and how that's changing over time. So one thing for the lab I wanted to show you guys before you guys get started, you're going to have to do some very simple statistical modeling. I'm making that sound a lot more complicated than it's going to be, but that's really what you're doing here. So I did a little example here, and this x-axis is just people, and the y-axis is going to be sales. So let's just kind of assume that I have a really small little business that I own, and for the past couple weeks I've been tracking how many people come into my business versus how much sales I have that day. And these little dark blue dots here, this is just my data points. So this is just showing you, like, if I have 5 people come into my store, I guess that's about like $27 or $28 worth of sales that day. Okay, so that's all these points. These are just different data points representing how many people versus how much sales. Now, based on these little points, it appears that in general, as I increase the amount of people in my store, the amount of sales goes up. It seems like that's kind of the general case. It seems like there's a pretty linear trend. And so because of that, I added this linear regression line in Excel. And again, if you should have done this in the human population lab, you should have added regression lines. So hopefully you know how to do this. If you don't, obviously reach out to me, or you can also go to the other Excel video that I posted and I showed you guys how to make these lines. But in Excel, you can also get the equation of the line. And that's what I have up here in the top right corner. So this equation right here is the equation of this dashed line. And so let's say I wanted to know if I had 30 people come into my store, how much sales would I expect to have that day? Now, I've never had 30 people come into my store before. The most I've ever had is 20. So you can see this is the biggest X value I have is 20. So what I'm doing here is I'm using this model that we created, this linear model. I'm using this right here to predict what my sales would be if I ever had 30 people come in. And so the way you do that is you literally just take your X value, which in this case would be 30, and you plug it in up here. That's literally all you have to do. So if we do that, you can see that I would expect about $54 worth of sales if I had those 30 people come into the store that day. So you're going to be doing stuff like this, but you're going to be doing it with this type of data, with this CO2 data, okay? So that is the basics of the greenhouse gases in the atmosphere. Like I said, this whole process right here is way more complicated than what we've talked about so far. We're going to get into a little bit more of this in the next lab after greenhouse gases, and it'll clarify some of this stuff hopefully. But again, if you're interested in any of this stuff, or if you want to know any more, any more of the complicated nitty gritty details of the stuff, reach out and I can send you stuff, or we can talk about stuff in Zoom or whatever. So that should be all you need for the lab. Again, make sure that you submit it on Blackboard and then also email it to me. And as always, if you have any questions, make sure to send me an email and I'll help you guys out. That's it.